This is the recording to determine the densities of the regular shaped and irregular shaped specimens that were used in the example that I videotaped. And so let me input the data. At the very beginning of the video I made a mistake, and when I talked about what kind of specimen I was using, and instead of taping it again, I figured, oh, I'm just going to use it as a teaching lesson later on to talk about experimental error and systematic error. So I'll get back to it later. At this point, I'm just going to input the data. So I measured the cube as 2.53 centimeters all the way through. We have an absolute error of 0.005 centimeters, and that is, take the last decimal here. I can only measure 2.53, 2.54, 2.52 with the caliper that I used, and then half of that difference from each of these is the absolute error. So I go half of 0.01, which is 0.005. I cannot be any more accurate than that, and that's what I'm going to put in here. I'm going to calculate the percentage error in just a moment. The mass was measured as 139 grams with an error of, again, half of the last possible digit. So half of a gram is 0.5 grams. That gives me percentage errors of 0.005 divided by 2.53. Oops. 0.005 divided by 2.53. Okay, and that here, because it's percentage, shift the decimal point twice, so it's 0.2% rounded. I'm not going to write down 0.1. I'm not going to write down 0.197%. I'm going to write down 0.2%. And for the mass, that is 0.5 grams divided by 139 grams, and that would be then a rounded 0.4%. So 0.2 for these three. And 0.4 for this one. Okay, then the density is calculated according to this formula, and of course the volume is length times width times height. So I multiply these three, that gives me the volume, and then I divide it into the mass, and that gives me the density. So let's see, 2.53, and then I have the luxury of saying to the third power, so 16.2 cubic centimeters. There's no space to write this down because I just want you to write down the density once you're done. So it's 139 grams divided by that result, and that is 8.58. And here I ask you, write down the result for the density as it appears on the calculator. Let's see, with a footnote which says this should exemplify that calculator results need to be rounded to an appropriate number of significant figures because the unnecessary figures have no meaning and create visual confusion, as you're going to see it in just a moment when I write this down. 8.58 3279142. That's what my calculator had. Total overkill, and in order to make a meaningful number out of it, it has to be truncated at some point. That's where significant figures come in, where exactly to do it, where to cut it off. Well, that's where it's helpful to look at the original data. This one is accurate to 3 significant figures, 3, 3, 3. That makes it easy to determine that the computed result needs to be 3 significant figures as well. Right there, 8.58. Okay, the absolute error and the percentage error for that result have to be determined as follows. Unfortunately, for determining a percentage error, it's a little inconvenient. It's in the addendum of this lab report, lab menu. You're going to do the following. Take the square root of each percentage error squared. So it's quite a bit of typing. I don't think too bad. So those are the 3 percentage errors for the length, width, and height, and then the percentage error for the mass. Either way, either do it the square this way or that way, and then take the square root of the sum. And again, what I just did here is in the addendum as well. Hit enter and I come up with a rounded 0.5%. Okay, and that in turn, that 0.5%, which is as a decimal 0.005, multiplies with the result of 8.58, and that gives me the absolute error of 0.0429. This should be truncated after the 4 because that's the last decimal for the computed result in the hundredth, so 0.04 grams per cubic centimeter. Okay, I'm going to write this in the conclusion. Here's what I would write. My result of 8.58 grams per cubic centimeters for, and originally I had mentioned in the video copper, compares to, and this is where the teaching moment will come up in a moment, compares to the accepted or theoretical value of 8.94 grams per cubic centimeter. Now, since my error was only 0.04, so I have 8.58 plus 0.04 for the density, but it should be 8.94, and you saw the specimen in the video, then I would say that my result should not be acceptable. It's just too far off. It's about 4% off rather than 0.4% from the accuracy. I used a caliper. I tried to measure to the closest gram, and it shouldn't be that far off. So for my error, I would say my measurements contain the following errors. So one too many R's there. There we go. Caliper, .005 centimeters. The balance, 0.5 grams. And these are, I'm sorry, random errors. and then I would have to look at actually zeroing the balance, and I think I did that at the very beginning. I'm going to write it down anyway. Tear or zero the balance, which if that wasn't done, that would become a systematic error. Or if I had used a measuring tape, then I could say, well, if I didn't align it exactly with the zero, then I also would have a systematic error. In this case, I did it pretty well, I believe, except my result was quite off. So I went back and I looked at the cube again and noticed that, whoa, that certainly didn't have the reddish color of copper, and I found out what my mistake was. I took it out of the box and it had the wrong label underneath. It said copper and it was brass actually, and then I guess the lighting in the lab that I used wasn't all that great, and I didn't pay close attention to it anymore. I just wanted to videotape. So here it is supposed to be brass, and the teaching moment is that I get a result that is too far off from what it should be. The result didn't satisfy me, and I figure out something must have gone wrong, and I try to fix that. So it was an experimental error that resulted in a systematic error, and so here I'm fixing it, and it's supposed to be brass, and I looked up the density for brass. I think you can read it here. It says 8.4 to 8.73 grams, and the reason why there's a certain range is that brass is an alloy of copper and zinc mostly, and so the properties of brass can change. The density of brass is in this range here, 8.4 to 8.73, so compares to the accepted value of 8.4 to 8.73 grams per cubic centimeter. And actually, if I look at this here, I picked that out from Wikipedia. I would say actually they should have put another zero here, because if this one is given to 3 significant figures, this one here should also be given to 3 significant figures. So I'm going to put that in there. And then you can see that, well, actually I did measure accurately, and my result is smack in the middle of where it should be. So again, I kept that initial mistake of misidentifying the specimen in there to show you that when something goes wrong, here is a way, in this case, to fix it. In this case, looking at that, oh, I used a different specimen. Next, we're gonna look at the irregular shaped specimen, and those were those steel screws. Oh, and I should actually say that here. Let's see, where was it again? There. This was brass, and that was the 8.4 to 8.40 to 8.73 grams per cubic centimeter. Okay, now let's do the irregular shaped specimen. So these were these steel screws, and the published value for steel is between 7.75 and 8.05 grams per cubic centimeter. Again, that's also an alloy. Okay, the mass measurement for those steel screws was 173 grams with an absolute error of 0.5 grams because I used the balance. The immersed or effective mass was 145 grams, and that was the effective mass. And on the scale that I use, the spring scale, I can only kind of see in the middle between two lines, which is between 140 and 150. That's where it measured as it was immersed, and I measured the effective mass of that, which of course is smaller because the buoyancy took, so to say, took weight away. And so it was in between 140 and 150, and I said that's 145, and then I would have to say, that could be still about with half of that error, with half of the 5, which around at 3. So that's how I came up with an error of 3 grams. Then again, determine the percentage errors. It's going to be 0.5 divided by 173, so that's 0.3%, and the other one is 3 divided by 145, and that's going to be 2%, so 0.3%, and I'll just say 2%. Yep, 2%. And then I do the calculation here. I have to go all the way back to the theory, which is here. This one here I didn't do. That's immersing the mass with water on top of the scale or balance. Here, this is the one I did do, where I had an extra bucket or beaker where the water was in and the specimen was hanging on a thread on that spring scale, and that's how I measured it. And the formula for that one is this one here: mass divided by mass minus the effective mass. So keep that in mind as I'm going to do the calculation here. So that's going to be 173 divided by 173 minus 145, parentheses, 6.178571429. Okay, now I have to see here, well, how many of these should I use? Well, technically I should use 3 significant figures because this one is 3 and this one is 3. I'm going to write down here for now 6.18. And then the percentage error, again, is that formula that you find in the addendum that says square root of, take the first one, the 0.3%, and square that, plus the other one, 2%, square that, parentheses, enter, and actually the percentage error remains as 2%. I could write it 2.0%, I guess. And then I take that 2%, change it to a decimal, 0.02, and multiply that with the computer result of 6.18, and that gives me an error of plus minus 0.12. 0.12 is the absolute error. Earlier I was a little bit hesitant to give it 3 significant figures. The reason is that in this calculation here I actually divide by 828. I think you can see that, which is actually 2 significant figures. So in this case here I'm just going to leave it at 3 because those are the original data, and if you give me one more significant figure, then necessary than would be required, that's going to be okay with me. Just don't give me all 8 of them, because this is just junk here. I think there are 10 listed here. So look at the data that you have, and that determines the significant figures. And as I said, if you give me one more, then alright, that's okay with me. Okay, when I look at the result here, 6.18, that one really is quite a ways off from 7.75. For that one, I don't have a nifty explanation like I did for the other one. And so here I just come up with that, well, my error on the second one was pretty large. And if you look at the calculation, if this one here was not a 145 but it was a 148 instead, then you can see that this one here changes drastically, 6.9 compared to 6.1. Still a little bit off, or still quite a bit off, but the error here actually is also relatively large. I know it's at 2%, but of the difference here, it might be actually larger than that. And then again, it also could be an alloy that is not in the original range or typical range. So this one here gave me a larger error, and it's a little bit unfortunate that for this particular one I couldn't come up with a better result. So I hope that for your data you're going to come up with some better ones than what I had. At least my first one here for the brass was right on once I had fixed it from copper to brass. But this one, yeah, what I say now here, how much was that? 7.75. 75 to 8.05. That's quite a bit off, and my measurements were as follows. Contain the following errors. I didn't use a caliper, I used a balance, and then I used the spring scale, and that one was about 3 grams. Those are random errors. Tearing or zeroing the balance, respectively, the scale. That means not tearing them, not zeroing them would be a systematic error. Then it's an alloy. Oh, that's what I should say for the other one as well, which is also a systematic error. So here I could comment that that measurement is right on. And here I would have to say that that measurement is quite a bit off. And I mean, maybe the explanation is that I thought I was using steel screws and I didn't. Respectively, that yeah, my errors here actually were rather large. This one here should go up there. And that could definitely have something to do with that.